I may have a late night tonight, but you can just let me know what you see or what you don't see. And if you see some alarms on the screen, please alert me if you're in class. Who knows what's going to happen now? But Unit 0 is the preliminaries, and that has two things in it essentially. Well, three things. It has an overview of control. If you want to read about control and what that involves, there's some history in the reading sections of an overview of control. There's also the syllabus, which we will talk about, and a passport assignment, which is your way into the class. To be allowed into the class, you have this passport, and this is really to make a connection between me and you. And for that connection to be established, I would like to first know your identifying characteristic, which is your name. And if you go by something other than your given name, give me your nickname and an email. Then a photograph, and this is very helpful for me because just tomorrow I'm going to have an interview with somebody that graduated or finished 5 years ago, and I'm not sure that I quite put the name with the face. I went back and found the passport, and now I know who I'm going to be speaking about to this interrogator. I swear to tell the truth, the whole truth. So hopefully that will go well, but providing me with a fairly up-to-date photograph helps me remember who you are, maybe beyond the semester. Now, to help me make that connection, you can tell me what food you like. And that's one of the items in this passport. When do you like to consume that food? And if it's something that I might not know about, it's helpful if I know the ingredients or how it's prepared, because I may not even know how to pronounce the food item that you like to enjoy. But give me a clue as to what you enjoy eating. I think we all, well, I enjoy eating, so I like to understand what others enjoy eating-wise. There's two more pieces of the passport into the class. One is a little reading for you, and that's to try to understand how we learn. And there's a book. How many have heard of Make It Stick? Okay. Well, it's not about gum on the floor and you're stuck. This is about learning, how to make learning stick in your mind. And there's 8 little chapter summaries that I want you to read, and then in response to reading those, you can respond to which of those chapter summaries do you think speaks to you after reading those 8, and essentially why. Then you need to sign the contract, and if you simply upload this into the D2L Dropbox, that's a verification of the contract. You don't have to worry about signing it physically. If you don't want to, or if you don't have the ability to scan it, don't worry about it. Just uploading it to the Dropbox or the assignment box in D2L tells me that you're in agreement. And now let's talk a little bit about the syllabus. Not a lot, but some. Are there questions on the passport? Syllabus, did I even introduce myself? Probably not, but I assume you might know me since you signed up for the class. But I'm Hal Tharp, and I will be your instructor for this class. Office hours will be held on the 5th floor of the ECE building in room 523, is that right? Yes, 523, and those are at 3 different days and at 3 different times. Hopefully one of those times or all of those times will work for your schedule. And one is right before the Monday class from 4 to 5. Another one is on Wednesdays from 12:30 to 2:30, and another time is on Fridays from 10:30 to 11:30. Some have asked about the textbook. There's a lot of material. I'm actually trying to write some chapters, so if I make create some chapters, I'll make those available to you, and you'll be able to read those also in addition. And those hopefully will be the most direct in terms of connecting with the material in this course. So I want to try to start uploading those. It may not happen today, but maybe starting tomorrow. And you'll find those on D2L, and I'll try to direct you to where those will be located, but probably they will be in the course resources unit and also maybe in Unit 1 and Unit 2 in terms of those units of material. What you may be interested in, here are the typical sections of a syllabus: the academic integrity, the library, non-discrimination, examinations. I'm planning to have 3 midterms and a final. Finals mandatory, and that's on the last day of finals if you're planning your semester. Last day of finals is May 10th, and it's at 1 to 3 p.m. on that day, the final exam. The other exams are each worth 20% of your grade, and those are listed there. And essentially, those are every 7 lectures, or after 7 lectures, we'll have an exam. And they are on Wednesdays, and they will be in this classroom for the people on campus. We also have homework that will be assigned. It will be available on D2L, and you'll submit it through D2L in an assignment box. And so you'll have to scan it and put it in as a PDF file. And for the 542 students, you will also have a project. And the 542 students, note that 10% of your grade is split between homework and project. For the 442 students, 10% of your grade is homework. You don't have a project for the 442 students. Here's a quick outline of topics, and you'll see these various places in different forms, but we're going to start the semester with modeling. How do we model systems, be those continuous time and or discrete time, or if it's continuous time, how do we convert it into a discrete time system? We'll do block diagrams. Maybe we'll talk a little bit about system identification, but then we'll also get into the Z-transform. And by the time we get down to Z-transforms, that will be exam 1. Then the topics, number of topics may slow down. The content may not slow down, but we'll have exam 2 and exam 3 mixed in there before the final exam. But we hope to cover these. And another way of listing that material is in these course outcomes, and I'm not going to spend time reading those or having you read those. You have time after class or between classes to look at these. I think there's 24 or so class outcomes, but you might read those and help guide you through what's expected of us in terms of what are we going to be responsible for on exam day. Questions on the syllabus? Yes. What does the 542 project entail? It will be something that you decide you want to work on, and that could be a paper that you're interested in reading and reviewing and maybe creating an example to accompany that paper. You might build something. You might build a device, and you're now trying to control that device. It's really up to you as a student, and so before you get too far into the project, you and I will agree on what you've decided you want to perform for your project. But it's fairly wide open. It might be a simulation on the computer. Like I said, it might be a hardware system that you're trying to control. It might be more of a analysis of a paper or papers that you're interested in becoming more comfortable with. Did that help answer? And most of the days we'll start with announcements, and then we'll have a list of goals, and then we'll start getting into the material. Your first homework assignment seems like it's forever away, but it's at the end of January, and I think that's a Monday evening. Your passport, did I say that anywhere? That's due the previous Monday, and that's really designed to try to get you comfortable with interacting with D2L in a way so that you can upload the material. If it becomes, and usually these are due at 11:59 on the due date, if it's 12:01 and something was hung up, I've created a generic Dropbox that you can put your material into because the D2L Dropbox will have closed by that time. But if something hiccups, you always have that generic Dropbox that you can upload to, and then I can see exactly when you uploaded to that Dropbox. But don't probably wait until 11:58 and try to upload something to the Dropbox. Some of these goals for today have already been accomplished. You've already signed in. If you're taking the online class, you don't have to worry about that. The passport assignment we've discussed the syllabus. Books and reading are in the course resources module. Those are all in the contents web page location of D2L. And now what I want to do is go over a quick introduction to why do we want to study digital control? Why do you need to be in this class? And then we'll actually start our first topic, which is system modeling for the semester. And if this doesn't look familiar to you, if you don't feel warm and fuzzy by seeing this image, hopefully before exam 1 you will feel very warm and fuzzy when you see a block diagram like this. How many here have already taken 441 or 541? Not as many hands. It's not required, but you've probably seen this, I hope, in an earlier controls class. If you've had a systems class or a signals class, maybe you've seen this, but I hope that you've all seen transfer functions. That's what that capital G of S represents. We will be learning how to design transfer functions in the form of controllers, these D of S's, or we will be doing it in discrete time and it will be a D of Z. And we'll be playing with the complex frequency variable S and the complex frequency variable Z, and we'll understand how those different complex variables are interconnected or related. And we then have all sorts of complex planes that we will be trying to think through as we move from the time domain into the frequency domain. Here, this is an analog control system, and I might call this G of S a system. I might call it a plant, and that doesn't mean that it gets placed in the ground and it becomes green and flourishes. It's just the terminology that we use in control. We call our system that we're trying to control a lot of times the plant. So we have our plant, we have our controller, we're feeding back the output signal, the Y of S, comparing that with a reference input. We may say, oh, this is an antenna and we want to train it or move it to point in this direction, point to a star, or maybe point to some other location. How do we command it? We say go to 20 degrees. And then we hope that our system moves over there smoothly. Maybe it overshoots, maybe it rings a little bit, but hopefully it gets there and we can maybe drive that error to a small value, maybe to 0. Maybe we can eliminate the error completely. What are some possible negatives relative to those analog controllers? It is living in an environment and it may actually not work very well due to those environmental conditions. The analog circuitry. Think of some board that you now have op amps, possibly resistors, capacitors onto that are implementing this controller's transfer function. That's your capital D of S. The components on that might age, or they might have You have different tolerance bands on your resistors. Those are also there for your capacitors. Maybe you have inductors. All of those tolerances may be kind of tricky to coordinate or to actually make work. And I will make these notes available to you so that you don't have to frantically copy them down, but I'll slow down and actually start probably writing my own at some point. But this is sort of a quick overview, and this one's more of a movie effect, and it's being shown to you as I scroll through it. The first part of this material on why digital control. There might be noise. There's going to be noise also in the digital system, but there might be noise entering in various locations on the analog circuit in that board that's producing or realizing your capital D of S. The parameters may drift. They may be expensive or unreliable. They may be heavy. They may be consuming a lot of volume, or their size may be bigger than what you want for your system. Maybe you now have a drone and you don't want that controller to be very big, volume-wise, weight-wise, etc. And if you've ever tried to put something onto a circuit board, there's maybe some debugging or soldering or interfacing issues that you have to worry about. Those all could be less than ideal with an analog controller that we're representing by this transfer function, capital D of S. And we would have to desolder or rewire or cut leads and wire jumper wires if we wanted to change something in that analog controller. Maybe we don't have a way of saying, oh, if this variable is actually higher than 5 volts, do something else. Oh, we would really have to design a very elaborate analog system to make those kinds of logic decisions, which if we have a computer, we can maybe more easily integrate those. Changes, like I said, or updates may be a little more difficult, trying to repurpose the analog board that's now realizing our controller. This is the sales pitch. So this class, we want to get rid of that capital D of S, and we want to replace it with a capital D of Z, which might be realized with a microprocessor, a microcontroller, maybe a DSP, maybe a computer, maybe an FPGA, but we have some computational machine that we will implement our capital D of Z with. That's for this class. We want to know, how do we build or how do we create this capital D of Z? Here is one such method. We really disconnect that capital D of S and we replace it with what's in this red hashed box. We're not changing our plant. That plant is still the same. The system is still the analog system, but now we need to interface with that analog system. And because of that, if we have a digital controller here and it's just blipping out numbers at discrete points in time, our analog system won't know how to respond to 2, 6.3, 7.2. It doesn't work with just these little, you have to hold them or give it a constant or a continuous waveform, and that's what this digital to analog converter does. If we're measuring an analog output, capital Y of S, and comparing that with a reference input, we're creating an error. And traditionally, we want to make that error small. Well, that error is still an analog or a continuous signal. We now need to convert it into a digital string of numbers so that we can process it with our digital machinery, our microprocessor, our computer. And that's where the analog to digital comes in. So we sample it, and convert it into a digital number, and now we simply somehow manipulate this input stream of air signals, which are this sequence of numbers, do some manipulation. And what is that? That's just a set of interconnected difference equations. That's what capital D of Z is in the time domain. That's just lines of code, and that outputs another sequence of numbers, which comes out as this, in the transform domain or frequency domain, this U of Z. We then hold that, and that now can drive this analog plant. Another scenario could be if we were working with a purely digital system. Now we have a system that is inherently discrete time, and an easy one to think about might be your bank account. You get a monthly statement, and so you could think of that balance as the output, and in that case, what do you want? You want that output to go unbounded. That's one of the few cases where you might like to see an unbounded response, right? You want your bank account balance to just go off the charts. That one you want to exponentially grow so that you can retire in a couple of years, right? That's what they were saying last year when I was in this class. They said, oh, I'm going to retire in 3 years. I go, okay, may I join you? I didn't get any takers on that one, but if you now have this digital system, you don't have to do the A to D and the D to A conversions. You can simply get this sequence of air numbers, do the manipulation on that in your computational machine, and put that sequence of numbers into your all digital or inherently digital system. Yes? Why is there an overbar on the capital D of Z? It was just to distinguish it from the other D of Z. I just didn't want you to think that they were the same. So it could be the same controller. It's just that you have two different ways of interfacing with your plant. So yes, I could erase that bar, or you could in your notes. It doesn't have to be there, but I'm just trying to show you that it doesn't have to be the same as what's up above. It could be the same. Obviously, we need to get comfortable with modeling systems. We have to be able to come up with these capital G of S's and capital G of Z's, which means, and we're going to focus on linear models, that means differential equations, which I'm assuming you've all completed. Maybe I won't ask for a show of hands because I don't want to know who hasn't had a differential equations class. You've all supposedly had a 320 class, a circuits class that covers Laplace transforms. It allows you to jump back and forth over this wavy line, to go from the time domain to the frequency domain, and we need to be comfortable going back and forth between those different domains. For example, what if we had a differential equation that looked like y double prime, that's now the second derivative of some waveform y of t or some analog signal, plus 4y prime of t plus 13y of t, and y of t actually might be our output. That's maybe what we want to drive to a certain location. Maybe that's an angle. Maybe that's a particular velocity in a vehicle. But we now would like to control that variable, that output y of t. And that might be driven by u of t. And here, hopefully by the context, you will know that what u of t is. Typically in this class, it's a generic signal. It's not the unit step. So don't confuse, and sometimes it is actually going to be the unit step, but hopefully by context you'll know what I'm referring to. In this case, U of t is our input that's driving the system. And now, if I give you this, can you give me the transfer function between the input U and the output Y? That's a test. Go. Can you? Can you give me G of S, which is Y of S over U of S? And now I should be seeing either frantic writing or head nodding saying, sure, I can do that. I don't want you bolting for the door saying this class is not for me. But if you are getting nervous, this is something you need to review and start to get comfortable with. What's the first thing you might start doing? So the constants go through, don't they? We are essentially trying to Laplace transform that differential equation because we're trying to go from the time domain, and I might be running between different spots in class just to emphasize the fact that we're moving into different domains. And for you that are working in the online or listening to this in the online version, you'll just have to get up and go to the kitchen, or if that's the time domain, and then maybe go into the, I don't know, where was I? The kitchen, maybe into the living room for the frequency domain. I don't know. But somehow you need to make this mental distinction between the time domain and the frequency domain. Here, it really just involves Laplace transforming. And the nice thing in getting the transfer function, what do you have to do with those initial conditions? I like this class because I can just walk around, right? I can come up here and play in the back corner while you guys are trying to derive your G of S. And I apologize for those that are online. They can't see me walking around. And I hope I'm not walking around in your apartment or your home. I'm not in the kitchen. But I have had students listening to videos late at night, and her mother walked down the hall and she goes, "Who's in your bedroom?" "Oh, it's just Dr. Tharp." There were calls to the switchboard. No, never mind. But maybe put your headphones on if you're listening to the videos of these so that you don't upset someone. Where were we? We were in the kitchen in the time domain, right? Worrying about what we were going to put on our passport for our favorite food. Or one of our favorite foods. We might have many. Just pick one. And you can flip a coin or roll the dice if you have 6 favorite foods. Somebody have a transfer function yet? What do we do with the initial conditions? We don't worry about them because we just want the dynamic behavior. We don't really need to worry about how it's going to respond to a particular set of initial conditions. So we neglect the initial conditions when we Laplace transforms. And that's the hardest part when we Laplace transform derivatives, is keeping track of these initial conditions. But to get the transfer function, we don't have to. In this case, what happens when we Laplace transform a derivative? It puts in a multiplication by s, doesn't it? What if we Laplace transform the second derivative? Now we have s squared. We're done. Now we simply, if we Laplace transform the left-hand side, we would have s squared plus 4s plus 13, all times capital Y of s, equaling Laplace transform of a generic signal little u of t is just capital U of s. That's the easiest Laplace transform you can have, right? You just have to hit the shift key and capitalize it. And change the argument. It goes from t to s. So don't mix t's and s's. If you're in the time domain, if you're in the kitchen, you can't also be in the living room. This new open floor mat or floor plan is confusing things, but there used to be walls that separated kitchen and living room. You separate those, time domain and frequency domain, but you need to smoothly move between them. So what's the g of s? Well, that now becomes 1 over s squared plus 4s plus 13. There is our transfer function. And if we wanted to know if I kick that system, and I'm going to be kicking systems a lot in this class, we want to know how is it moving. How does it move? Well, it moves in response to where those poles are located. So if you found the complex plane location of those poles, that tells you something about how quickly those modes decay and how they shake, how they oscillate, the roots of a quadratic. We also need to learn how to model in the digital domain. And now we have both domains. We have time domain and frequency domain. In the time domain, we now don't have differential equations. We have difference equations. Now we might have something like y at sample little n plus 2. And then we might have a collection of delayed or advanced output signals, y. So this n plus 2, I will probably routinely suppress the sample period, capital T, but this means n plus 2 sample periods in time. That's the actual time that we're at. And let's say that this is now minus 0.4 y of n plus 1 plus 0.1 y of n. And again, this is our output, which might be a sampled version of the analog signal y of t. And I've run out of space, but this is now equal to an input, u of n. And this is now our input. How many have seen a z-transform? That's not a requirement to get into this class, so I don't have to kick everyone out that I didn't see a hand raised. We'll learn how to do z-transforms before exam number 1. But we do it similarly. Now we enter into the z-domain, the frequency domain, and essentially these advances and delays in our arguments of the inputs and outputs correspond to z's, powers of z, and delays z to the minus 1s. Here we have advances, so this now converts into a g of z The process is similar. It's the z-transform of the output over the z-transform of the input, and that ratio now becomes 1 over z squared minus 0.4z plus 0.1. And you will become, by the end of this semester, very comfortable knowing where those z-plane complex poles are and what that corresponds to in terms of how that system shakes or how it moves. And obviously the z-plane is different from the s-plane, but they're both complex planes. And we'll understand the connection between the z-plane and the s-plane. We will also have to become very comfortable converting or moving back and forth between these different representations. Time domain, frequency domain, continuous time or analog, discrete time. We need to become very comfortable with all of those modes of modeling a system. Now, here is a review. Let's go through the modeling of a continuous time system. And since I'm assuming most of you are ECE, electrical and computer engineering backgrounds, I'll give you a circuit. Suppose that we now have the following circuit. Here's a voltage source that has a generic input, U of t. That's not the step, unit step. It's just a generic input waveform, U of t. We have a resistor. We have a capacitor. Maybe that's not quite enough. Let's just keep going. Here's another resistor, another capacitor. And now I want you to come up with the differential equation or coupled set of differential equations that model that system. Or can we find the transfer function that connects certain variables? And let's just pick something. Let's say that our output is that voltage dropped across that second capacitor, C sub 2. If I covered up R2 and C2, or if I erase those, what would I have with R1 and C1? What kind of a system would I have? If we didn't worry about R2 and C2, so you can virtually erase those, what do I have if I have that voltage source with R1 and C1 in series? Is that a filter? Is that a filter? Is it a filter? Yes, it is a filter. Now, what kind of a filter is it? What kind of filters do we play with? We have low pass, we have high pass, we have band pass, we have band reject. Oh, gosh. You should have had this in 320, right? This is low pass. This is a low pass filter. So now we have a couple of stages that are like low pass filters. We already sort of know what we should be seeing when we start simulating this. And that's a way to check. That's sort of the answer in the back of the book. If we start deriving the equations that govern the dynamics of this circuit, we now have a way of hopefully connecting that with our gut feel of what should be happening with that system. How would we come up with, let me just say, a coupled set of differential equations for this circuit? Does that make you feel warm and fuzzy when I start saying coupled set of differential equations? And here the head should just be going rapidly, yes, we're experts at this. And if not, you have a 3-day weekend to become experts at your 320 material. And there's all sorts of review material on the preliminaries and review unit. Did you learn how to select variables that you want to write your equations with respect to? If I give you a circuit, how do you now start finding or identifying variables that you want to write your differential equations in terms of? Have you heard of state variables? Have you heard of energy storage devices? Do you have any energy storage devices in this circuit? The capacitors are storing energies, aren't they, in the electric field? We're charging up those capacitors. And does that happen instantaneously? No. There's a differential relationship between current and voltage on a capacitor and an inductor. Who's heard of Eli the Iceman? And it's a little bit cold today, so we want to use ice, or we're using ice. It's cold in Tucson. It's below 60. For those of you listening that are maybe somewhere other than Tucson, I apologize for making such a dig at the temperature, at the cold temperature in Tucson. It's going to warm up, I think, right? I have a heavy jacket, the heaviest jacket I have, and I wore it today, and it's barely pushing 60. Whew, That's pretty sorry. Anyway, where were we? We were in the time domain. We were in the kitchen worrying about energy storage. Energy storage devices, which are our capacitors. So let's now write these equations in terms of these state variables that I'm now defining. And I wanted that to change color to the capacitor voltage because I'm now worrying about ice in the Eli and ice, and that's because this tells me the governing differential relationship between current and voltage of my capacitor. From ice, I know that the capacitor's current, I sub C of t, is equal to C, the capacitor's value, times the voltage, that's the E, the electromotive force, but here I'll just call it D of V sub C of t dt. And now I have a way of expressing the current through both of those capacitors in terms of the voltage, the differential voltage of those capacitors. I know the current going down through C sub 1 is I sub C sub 1, but I don't want it written in terms of that. I want it written in terms of the voltage. So it's going to be C sub 1 dx sub 1 of t dt. And I now have a way, I have two energy storage devices. I should be expecting a second order set of equations. Two first order coupled differential equations will actually result from the way I'm analyzing this circuit. So if I looked at the transfer function of this circuit, it's going to have a second order denominator or an s squared downstairs eventually. I'm going to now write two KCL equations, Kirchhoff's current laws, at these two nodes. Let me call this node 1 because it's touching R1 and C1, and I'll call this node 2, which it's touching R2 and C2. And I may have you try to remember what's going on, but let me say that now coming out of, if I write KCL at node 1, I can say, oh, all the currents leaving that node have to sum to 0. How many currents do I have? I have this current going to the left. I have a current going down through C1, and I have another current going right through R sub 2. I just need to find equations for those three currents in terms of U, X1 and X2, and algebraically sum them up relative to how I've drawn those current directions in that circuit relative to node 1. And that's my first differential equation that will involve x1, x2, and the derivatives of x1 and x2, potentially, and maybe the input u. What's the current going from out of node 1 through R1 in the positive direction that I have labeled there? How would you define that current? Now I hide it from you and you have no clue. But at node 1, what is the KCL equation?
Negative U of t times R1.
So now, what is the response was negative U of t over R1. Is that correct? So we need to figure out what is our voltage dropped across that resistor. So U is a part of that. The input is playing into that, isn't it? And it will come in as a minus U of t. But we are worried about the drop across R1, let's say from the right-hand side of R1 to the left-hand side. That's the positive drop, the way I've drawn my arrow. And that drop is actually x sub 1 minus U. There's the minus U. Is that So the voltage dropped across R1 is X sub 1 minus U. There's our minus U. Do we see where that's coming from? And now how do I get the current once I have that voltage? It's dividing by R1. So now I have that current is X1 of t minus U of t over R1. That's that current going to the left. So there's the minus U over R1. We almost had it. What's the current vertically going down in the positive direction that I've indicated through that capacitor? That's ice, isn't it? That's C dV dt. So it's C1 dx1 dt. That's now the current going down, and we add that. So now I have plus C1 dx1 of t dt. Or you might see me calling this x1 prime of t. And I now just have one more current to sum, and it's now the current going to the right in that positive direction through R sub 2. What's the voltage dropped across R sub 2, positive side being on the left of R sub 2 and the negative side being on the right side of R sub 2? X1 minus X2. And to get the current, I just divide by the resistance. I now have then plus X1 of t minus X sub 2 of t. And that 0 doesn't need to be minimized, but I was running out of space. Actually, I have an infinite page to the right, but I know you're constrained with 8.5 inches probably. But that's now all equal to 0. We're comfortable with that KCL equation at node 1. If you're comfortable with that, it should be fairly straightforward to find the node 2 relationship. Let me do that in a different color. Maybe now I have this current and that current added together, and they algebraically sum to 0. That red current going to the left through R sub 2 should just be the negative of what we found for the blue current, and that's just X sub 2 minus X1 over R sub 2. And plus current down through C sub 2. That's ice again, isn't it? C2 dx sub 2 dt. There's our second equation, the node 2 equation. We have X sub 2 minus X1 equaling 0. Now, that's our set of dynamic equations. We have two first-order differential equations, and they're coupled because we have x1s and x2s floating back and forth between those, or not floating, but they're in those two equations. That's the dynamic behavior. That's how the system shakes. If I give you R's and C's, you know how that system is behaving. What's the output equation associated with that system? Now I want to write y of t in terms of the state variables x sub 1, x sub 2, and the input u. This one's so easy, sometimes you miss it. But y is just x sub 2. We just defined the output to be the voltage across that second capacitor. We could pick an output that's some linear combination of a lot of different variables, but here we just said, let's call our output the voltage dropped across x sub 2. So in this case, y of t is simply x sub 2 of t. In general, it could have been something else. We may want to convert that collection, our dynamics and our output, into a state space representation, which is very straightforward now that we have these equations already available to us. Now it just requires some algebra. To get our state space representation. So that now x1 prime, we just solve, we find this equation that involves x1 prime, and we isolate it and put everything else on the other side of the equal sign. And that will give us our state space representation. We want the right-hand side to just have state variables, in this case x1 and x2, and inputs, u, and not involve their derivatives. In this case, we simply divide everything by c sub 1 and push everything else on the other side of that equality sign. And that now gives us an equation for x1 prime, which ends up being minus 1 over r1 plus 1 over r sub 2. We were dividing everything by c sub 1. That's scaling x sub 1 of t. Then we had something scaling x sub 2, which was just 1 over r sub 2 c1 x sub 2 of t. And going up here was the input piece, which was 1 over r1 c1 u of t. So this is also on that right-hand side. That's our first equation in our state space representation. And if that was a little quick, you can do that tonight when you go home in your kitchen, because we're in the time domain. I don't care where you do it, but this is a differential equation, and now you have a way of writing it. We can do the same thing to find or solve for x sub 2 prime of t, and that becomes not quite as many terms, but the same process. We divide everything by c sub 2 now and isolate x sub 2 prime. And that equation doesn't contain an input. The input indirectly comes into play with the dynamics of this voltage across that second capacitor, because these equations are coupled. We have an x1. An x1 is dynamically influenced by x1, x2, and the input u. So these two equations are interconnected, and the input then does influence x2, but not explicitly. It does it through the coupling. But the input is driving that set of resistors and capacitors. And our output equation hasn't changed. That's just x sub 2 of t. That's one way of describing the dynamic behavior of that RC circuit. What's another way? We could also do this as a block diagram. What is this block diagram trying to do? It's actually trying to solve that coupled set of differential equations. And how do we do that? We put it into an analog computer. How many have an analog computer at home? No one? There's actually an analog computer picture in the conference room in ECE. If you want to know what in the world is he talking about, what's an analog computer, it's really an interconnected set of integrators and gain blocks and summing junctions. And you can wire those up and solve differential equations. Yeah, I had to write up the lab for that. I played with analog computers. That's dating me, isn't it? But it's really a good way to understand differential equations. Now you can interconnect these op amps, gains, and summing junctions based on what the differential equations tell us and solve a differential equation or a set of coupled differential equations. That's our block diagram. We want to now become comfortable with what I will refer to as all integrator block diagrams. How many integrators do you think I need in my block diagram to solve this system of differential equations? How many derivatives do I have? I have an x1 prime and an x2 prime. If I can integrate those, I'll end up with x1 and x2. I need two integrators. And I'm going to interconnect those so that x1 prime is the input to one of my integrators, x2 prime is the input to the other integrator. The outputs of those integrators will be x1 and x2, because if I from calculus, if I integrate x1 prime, I get x1. If I integrate x2 prime, I get x2. Don't you wish calculus was that easy? You could have been playing with integrators on your breadboard. How do you make an integrator? Oh. Pardon?
This one's actually covered in 320.
Somebody said it was covered in 320, which is good. We're remembering. I don't know where it was covered. Maybe we covered it in 320. But it's what? It's an op amp and a capacitor and a resistor. So if you want to build an integrator, it just takes an op amp, a capacitor, and a resistor. We won't worry about that, but we will just draw it and say, here is my integrator. That block is integrating. And I'm going to put into that the derivative of x sub 1. If I put x1 prime into the integrator, what's coming out? x1. So now I've produced x1 of t. I can do the same thing to relate or to help me solve x sub 2 and x sub 2 prime. I'm going to have now a second integrator. And now I have x1 and x2, and I know how to interconnect those from my differential equations. I now need to make x1 prime be this combination of scaled x1s, x2s, and u's. So my resistors and capacitors are my gain blocks, and x1 and x2 I have coming out of those integrators, and U, I'm assuming I have access to. That's my externally supplied voltage supply. Memorize this, and we can now build the interconnected structure of this all-integrator block diagram. X1 prime is now going to be the output of a bunch of signals coming into a summing junction. One of those signals is going to be a scaled version of the input, and the scaling there's U of t at the input scaled by 1 over R1 C1. And what else? Well, I had a x1 scaled by that gain block, and I had an x2 scaled by that gain scaled x2. Those three signals put together produce x1 prime. That's now my part of my block diagram. Do you now know how to build the rest? We just go to the second differential equation and say we need to make x sub 2 prime out of x1, x2, and u. X sub 2 prime had x1 scaled by 1 over r2 c2, and it also had a minus 1 over r sub 2 c sub 2. And there is my all integrator block diagram. That's my analog computer that will solve that coupled set of differential equations. If I know my r's and I know my c's and I know my input u, the output y will be the solution to that coupled set of differential equations. And that's now an analog computer. Yes? So why am I calling it an all-integrator block diagram? Because it's got summing junctions and gain blocks, but the dynamical piece of the block diagram is made up only of integrators. I don't have any way of I don't want to differentiate. Why do I not want to differentiate? Suppose I had a noisy signal. What happens when I differentiate noise? Gets worse, doesn't it? I'm differentiating something that's going like this, and what's the derivative? It's taking the rate of change of that. It's making it even worse. So I want my analog computer to be built from integrators that help solve these differential equations. So I just call it an all-integrator block diagram. Now, this was in the kitchen, was it not? This was in the time domain. And I'm going to forget what room I'm in, but you can remind me, hopefully. But this is now the kitchen. This is the time domain. What if we wanted to build a block diagram in the frequency domain? How do integrators get transferred into the frequency domain? What was an integration operation in the Laplace domain? Do you remember what you needed to do in the frequency domain to integrate? What happened when we differentiated in the frequency domain? When we Laplace transformed y prime, what happened in the frequency domain? It was a multiplication by s. What's the inverse operation of multiplication? Dividing. So now when we take this block diagram into the frequency domain, which will allow us to directly find our transfer function, we will simply be replacing these integrator blocks with 1 over s blocks. And any signals that we have won't have t's for their argument, it will have s's. We've now moved into the frequency domain. We can now draw a block diagram in the frequency domain using exactly the same structure. It's just now those integrators become 1 over s's. If someone in your job interview gave you this analog computer simulation and they said, can you put this in the frequency domain? You can go, yeah. You wouldn't say that. You would just say, yes, I think I can. And then you would just draw it right out, right? Because all you have to do is copy exactly what was up there Except now let me make it a little easier. Instead of writing all these coefficients, let me call this alpha 1, 1. This let me call alpha 2, 1. This one alpha 2, 2. And this one alpha 1, 2. And let me call this beta. Now I don't have to write so many expression or constants. But these will now fit in my state space representation also, these alphas and betas. Now I have in the frequency domain, I still have this beta going into an integrator, which in the frequency domain is 1 over s. And what's coming out? The Laplace transform of little x1 of t, which is capital X1 of s. This now gets scaled by alpha 2, 1. And now you have the job. You've now passed the interview question. You now have this block diagram in the frequency domain. Has exactly the same structure. The only difference that I've made is I've now assigned those blocks to have simpler coefficients. Now I've just become Greek in my lettering. But it's exactly the same thing, which allows us to conveniently write another time domain expression, which is a matrix representation of our state space representation. If I wanted this, the state space representation, I had two state variable components. I had an x1 prime and I had an x2 prime. Now I just stack these state variable derivatives up in a column vector, and that's my state vector differentiated. I now need to make that equal a linear combination of state variables, x1 and x2, and input u. And all of this has to be compatible, meaning what do I have on the left? What kind of a vector? What's the dimension or size of that vector on the left of the equality? That's not a hard question, I hope. It's a it's 2 rows tall, and how wide is it? How many columns do I have in that vector? I just have one column of numbers, right? So it's a 2 by 1 vector. Whatever I have on the right, if I have a combination of a product of matrices, the result better be a 2 by 1 vector. Meaning, if I now have some matrix that scales x1 of t and x2 of t, what are the dimensions on this x sub 1 of t, x sub 2 of t vector? Matrix. It's a 2 by 1. It's a vector, isn't it? So now I need to have something multiplying a 2 by 1 vector giving me a 2 by 1 vector. What's that something's dimension? 2 by 2. And that's my alphas. This is actually, and if you go back and plug all of those coefficients in the right way, there's my alphas. Plus something times my input. The input was just a scalar. It was a 1 by 1 matrix. I need a 1 by 1 multiplying something to give me a 2 by 1 vector. What's my input matrix going to look like, matrix-wise? What are its dimensions? How many rows does it have to have? It has to be compatible with the left-hand side. It has to have 2 rows. How many columns does it have? Well, it has to be consistent with the scalar vector on the right that's multiplying it on the right. So how many columns does that matrix have to have? It can only have one. So my input matrix is 2 by 1. What do I put in that matrix? Beta in the top row and 0 in the bottom, because I didn't have the input directly coming in to that second equation. This matrix we may call the A matrix or the system matrix. This is our capital B matrix or the input matrix. And our output equation is going to be something times our state vector plus something times our input vector, which in this case, or matrix, and it's a scalar, it's 1 by 1. How big is my output? How many output components did I introduce in that circuit? 1. It's a scalar. It's a 1 by 1 matrix. So whatever is happening on the right-hand side of that equality, when I perform that multiplication, I better end up with 1 by 1 matrices or scalars. The first piece, I have to now multiply something times a 2 by 1 vector to give me a 1 by 1. What's that matrix dimensions going to be? 1 by 2. And what was our output? X sub 2. So now I need these entries picked in such a way that I just pull off X sub 2. And what are the dimensions on my matrix that multiplies U of t? How big is U as a matrix? 1 by 1. How big is Y? 1 by 1. What do I multiply a 1 by 1 by to produce a 1 by 1? A scalar, Tharb. Come on. So this is just a 1 by 1 matrix. And what's in that matrix? There was no U directly feeding in or creating our output. This was now just a 0. And we give these, logically enough, you've learned your ABCs. This is A, B. What do you think this is? C, and this is D. So these are our output matrices, C, and our direct feed-through matrix, D. And what we want to do is now go into the living room. Bless you. We now need to get into the frequency domain and make this a transfer function in terms of A, B, C, and D. You can think about that over the long break. No, it's not a break. It's a weekend. Have an enjoyable weekend. Did I announce no class on Monday? I probably didn't need to announce that. I will see you in a week. Enjoy the rest of your first week of class.